Fast Physics, where I go quickly over topics in physics. My name is Maggie, I'm 15, and in my personal opinion, I have fairly large ears. But anyway, there's no intro for this video because we're going to be covering a lot. Today we're going to be deriving the kinematic equations, which are equations for motion in one dimension, where acceleration is constant. I introduced them along with a mnemonic device for remembering them in my last video, which you should check out if you haven't yet. So there are a few things that we need to know before deriving our four most common kinematic equations, but they're mostly just common sense and the definitions of displacement and acceleration. First of all, acceleration has to be constant because it allows us to assume that average acceleration and instantaneous acceleration are equal. Remember that acceleration is change in velocity over time, so we write it as a difference between final and initial velocity divided by time. Let's think back to a few videos before when we were discussing your charge on Area 51, the one where you actually made it inside. If we take the average acceleration of all 8 seconds, we get 0.3 meters per second squared, which is the final 5 meters per second minus the initial 3 meters per second divided by the 8 seconds in which it happened, right into 1 sig fig. That's obviously not the same as our instantaneous acceleration at certain points on the graph. If we take a look at the first 2 seconds, you didn't accelerate at all because your velocity didn't change, but then you accelerated at 1 meters per second squared for these last 5 seconds. That last part's acceleration was constant, so we know that the instantaneous acceleration at any point along those 5 seconds should be the same as the average acceleration of that period. For example, for this second right here, final velocity 3 meters per second minus initial velocity 2 meters per second divided by the 1 second in which it took it to occur gives us 1 meters per second squared, which is the same as our average velocity for that period. A final 5 meters per second minus the initial 0 meters per second divided by 5 seconds also gives us 1 meters per second squared. Let's also remember way back when we were talking about how finding the area of the space between the x-axis and the velocity timeline gives us displacement, because velocity equals displacement over time. Just by knowing that, we can make our dtv triangle over here, where time is displacement divided by velocity, and displacement equals velocity times time. We can write that last one as delta x equals velocity times time, which really just makes sense when we look at it over here. Finally, we need to know that average velocity equals final plus initial velocity divided by 2. That's pretty self-explanatory, right? If my sister and I are taking the average of our money, and I have $5 and she has $7, we each have an average of $6. Let's put all those things together to get our kinematic equations, shall we? Let's do them in the reverse order of our mnemonic. Both with half of the 80s being displaced by a tail of 2 squares and 2 axes. The last 5 are only the first 5 at the end. So, the last 5 are only the first 5 at the end. That's v sub f equals v sub naught plus at. We can just start off with the literal definition of acceleration for this one. Acceleration is the change in velocity over a certain period of time, so just the difference between the final and initial velocities over time. If we solve for the final velocity and multiply both sides by t, then add initial velocity on both sides to move it over, we get the final velocity equals acceleration times time plus initial velocity. By the commutative property, we can switch acceleration times time and initial velocities places because they're being added to each other to get that final velocity equals initial velocity plus acceleration times time, which is our first kinematic equation. Now that we have that one, we can build our other kinematic equations off of it. Let's keep going with the mnemonic. A tail of 2 squares and 2 axes. That's v sub f squared equals v sub naught squared plus 2a delta x. Let's start off with our mini equation for displacement here, where displacement equals velocity times time. Now let's move our first equation down here and start solving for t. Move the initial velocity over by subtracting it from both sides and then divide both sides by acceleration. To get the time equals final minus initial velocity over acceleration. Let's substitute time in our equation up here with final velocity minus initial velocity over acceleration, and then substitute velocity in our equation up here with average velocity, which we found earlier was final plus initial velocity divided by 2. We get that displacement equals this binomial up here, divided by 2 times acceleration. So let's move it to the other side by multiplying both sides by it. It cancels out on this side, leaving us free to work out this binomial. Let me work it out really quickly in case you guys need to see it worked out. This times this, so it's squared, then v sub f times negative v sub naught, so we have negative vf v naught, then positive v sub naught times v sub f over here, which is positive vf v naught, then finally positive v sub naught times negative v sub naught, which is negative v sub naught squared. These two cancel each other, so we're just left with v sub f squared minus v sub naught squared. Let's put that back into our equation, where we now have that 2 times acceleration times displacement equals v sub f squared minus v sub naught squared. If we just add v sub naught squared to both sides, these two cancel out, leaving us with 2a delta x plus v sub naught squared equals v sub f squared. If we just switch the 2 sides of our equation, we got our equation as it appears up here and in most other places. So now we're at the first part of our mnemonic. But with half of the 80s being displaced, or v sub naught plus 1/2 at squared equals delta x. Now let's go back to the first equation we found earlier, and let's add initial velocity to both sides and divide both sides by 2. Add the v naughts, these two become 2 times v naught, then divide both sides by 2. So the 2 appears cancelled out. Remember that this didn't change the meaning of the equation at all, because we performed the same operations on both sides of the equation. But an interesting thing that we're seeing right now is that on the left side of the equation here, we have final plus initial velocity divided by 2, which we know from earlier was exactly our definition of average velocity. We can replace it with that. So now we have a new equation for velocity. Let's put that equation for velocity into that mini equation for displacement. Replacing velocity with v sub naught plus 1/2 acceleration times time, and distribute everything properly. That's displacement equals initial velocity times time plus 1/2 acceleration times time squared, which is exactly the equation that we see above. This video is getting a tiny bit long, but let's quickly get that last equation too. It's not mnemonic because to me it's just so easy to derive. It's displacement equals final plus initial velocity divided by 2 times t. We get it once again by seeing that displacement equals velocity times time. We can replace that change in velocity with average velocity because we know that acceleration is constant. So let's substitute final plus initial velocity divided by 2 in our equation for velocity. And that's it. That gives us displacement equals final plus initial velocity divided by 2 times time. Okay, so that was a lot. I hope that this video helped you guys in deriving the kinematic equations, and that it made my weird mnemonic from last video a little bit less weird and a little bit more practical. If you want to see other people deriving the kinematic equations, I know that Tangerine Education has a video on it, and so does Doc Physics. I definitely also recommend the AP Physics collection topic on it, which is a lot more in-depth than my explanation was. It's not a video, but you know, reading ain't never hurt anyone. But thanks for watching this video, and don't forget to like it and subscribe to see more of my videos. Bye!